Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is going to be to describe how to write what are called equations of motion for particles under various circumstances. Now, the particle we're going to look at in this example, we're going to look at this automobile here. And the first thing we're going to do is we're going to talk about, I'm going to call this case 1 here. Acceleration is 0, velocity constant. So, imagine this automobile, whoops. Just, moving down the road at a nice constant speed, like so. All right, so I'll put it back to the starting point here. Now, I don't know why I got that line down the middle, but the first thing we do when we're trying to track a particle, the very first thing we do is we've got to put a coordinate system in the problem. Oops. So I'm going to go ahead and do that. We got the ground here. Oh, the symmetry button is on, doggone it. There we go. Car presumably is not floating in midair. And I'm going to go ahead and put a coordinate system in. You can put a coordinate system anywhere you want. I'm just going to put it over to the left here, just because that's where I feel like putting it in this video. Alright, so X, Y. And again, I like to use two-dimensional coordinates as a rule of thumb, because most problems we look at in physics are going to be two-dimensional. So now the X coordinate of the car is the distance from the origin to some point on the car. I'm going to put that point right here. So this is what we're calling X. Now, if the velocity is constant, then the velocity graph is kind of boring. All right, so again, if we graph velocity against time, then that graph is looking something like this. Now the idea here, though, is if we want to write equations, I'm going to carry this graph out not to like 2 seconds or 5 seconds or 10 seconds. I'm going to carry it out to kind of a generic time here that I'm just going to call t. The position graph now, if we sketch that one, I need a little more room here. The position graph is now going to be linear in this example. So X against t might look something like this. Now, this one doesn't start at 0, 0, and that's by design. Because of where I put my coordinate system origin, at t equals 0, the car has an initial x coordinate. I'm going to put x sub o for that value. This can be some number in the problem. It can be 20 feet, 30 meters, it can be anything. Whatever this value is, that's going to equal this distance on this graph. Now, as far as the equation that describes the position here, there's a couple ways to get it, and I'm going to talk about using area. So hopefully you've seen my graph on how to calculate the change in position or the displacement for a particle from a velocity graph. The change in position, the delta x for that car, is going to be given by this area right here. Now this is a nice rectangular area. The horizontal distance I called t. This distance I don't have labeled yet, but this is going to equal whatever the initial speed of the car is. I'm just going to call that v sub o for now. And that's going to be whatever that car's speed is moving to the right. Therefore, the change in position, the delta x, is equal to this area, which would equal v sub o t. Now, delta x. Change in anything is always final minus initial. So this delta x can be written x final, which I'm just going to call x, minus x initial, which is what I call x sub o here. And we could just solve this now for x by adding the x initial to the other side. So the equation for this line is going to look something like this. X, this is going to be some function of t, is going to equal x sub o, wherever the car starts. In this problem, that's going to be this distance, plus v sub o t. If you're in a physics class right now, whoever's watching this video, and you look up under one-dimensional motion, you'll find what are called the kinematic equations, and this is one of the kinematic equations of motion. It's the position function for an object undergoing an acceleration of 0. I like to work these problems on kind of a case-by-case basis and go through and develop equations for each example, treating each case kind of uniquely. So there's case one, zero acceleration. You end up with a horizontal velocity graph, a linear position function, and that's how you find the equation of the line. All right, now we're going to look at case two here. I'm going to get rid of, actually I'll just use an eraser. Oops. All right, so case two is going to be this. Car starts from rest. However, the acceleration isn't zero. It's some value. I'm just going to call that value A. It might be 2 meters per second squared, it might be 7 meters per second squared, it might be 16 foot per second squared. So now I'm going to go ahead and, just to remind me that we've got an acceleration in this example, I'm going to go ahead and draw the motion diagram for the car. So this car starts from rest and starts accelerating to the right. Again, this dot's going to start getting further and further and further apart. And I'm going to go ahead and put some vectors on to describe this as well. So the velocity of the car here might be represented by this length, but that velocity vector is getting larger and larger and larger. So again, these are velocity vectors. In this case, we're going to assume the acceleration is constant. So if I drew acceleration vectors at the same locations, they might look something like this. Now you notice that I'm trying to draw these acceleration vectors roughly the same length because I'm trying to go through an example of a constant acceleration. And you might wonder, if you look at this pair and say, well, why is this acceleration bigger than this velocity? Well, that question doesn't really even have any meaning. It doesn't even make sense to compare a velocity to an acceleration because they're not the same thing. It would be kind of like saying that the color red is more than 2 square meters. That just doesn't make any sense. In a similar sense, it doesn't make sense to say that a 3 meter per second squared acceleration is more than 2 meters per second. It doesn't make sense to compare them because they're not the same thing at all. Right? So now, if our acceleration is constant, and this car started from rest, so case one was, I'm sorry, we're at case two here now, aren't we? Constant acceleration, but initial velocity is 0. Our velocity graph is now looking something like this. Now, as far as finding the equation for this line, we can do that just by writing out what acceleration is. Acceleration is change in velocity over change in time. If I solve this for the delta v, we get acceleration times delta t. Now, change in anything can be written final minus initial. So this change in velocity can be written v final minus v initial. But in this example, the v initial is 0. And then 99 times out of every 100 problems you work in physics, normally your t initials will be 0. So this delta t, really we can just write as t because it's going to be t final minus 0. If we solve this for v, we just get acceleration times time. And that's the function that describes this curve, v equals at. That's a linear function with no intercept. Okay, now, our position graph. So because the car is moving faster and faster and faster, this graph is going to have some concavity to it. So this graph might look something like this. And there's some sort of function that describes this that we're going to find here in a moment. Now the key is you have to think kind of generically. Think about this curve out to some generic time, some point, we'll call that t. Same thing up here, out to some t. And then this distance on the graph is x, which is a function of t. And here's how we get at this guy, that function. Remember that the displacement, delta x, we can get from the area bound under this curve here. So this area right here is going to equal the delta x. This distance is t. This distance is described by this function, and one way to write it is acceleration times time. So this area is 1/2 t times at, which ends up being 1/2 at squared. Now, delta x, remember, is x final minus x initial, so I can write this x final, which I'm just going to call x, minus x initial equals 1/2 at squared. And we can put this x initial on the right for aesthetic reasons. And there's what this function looks like. It's quadratic and opens up. Now, I went through these examples without numbers. We didn't use a numerical example for the x sub o or the acceleration. I'll go ahead and do some numerical examples in the next video. But this is basically how you write the equations of motion for a particle. I like to start with a velocity graph. You can usually get the equation for that velocity graph from the acceleration pretty easy. Then you use the area under that curve to get an equation for the position graph. Now, I think I'm going to just end this video right here so it doesn't get too long, and I'll look at the more difficult cases in other videos. Hope this video helps demonstrate how to do these things. Have a great day.